Take it away.
All right. Thank you very much. I'm very happy to be here to talk about this recent work I did about trying to generalize ideas of GKP code, but with a measurement kind of included in these codes, so they will evolve with measurement. And so we know maybe more about them with Floquet codes. So these are different names that we generally use, but I will describe these codes in the concept of GKP. So maybe just an example of a dynamical code, which is the honeycomb code. It looks really much like a surface code where we want to measure the plaquettes. And the most straightforward way to do that is just actually adding an ancilla and then trying to connect everything there and measure. Another thing that we can try to do is actually separate these measurements into three sequences of measurement. And so we kind of reduce the amount of connectivity that we need. And then the circuit that we need to measure those actually reduce, so we get shallower circuits. All right. So we kind of get the reduced weights of the stabilizer that we need to measure along the way. Yeah. Oh, yeah. This one. All right.
Yep.
Hi. No. Can you hear me? Oh, yeah. Perfect. All right. So yeah, using this sequence of measurement, actually we can reduce the weight of the stabilizer that we need to measure. And so we introduce less errors in general using these shallower circuits. So this could be an advantage in general for dynamical code. Another example of how we can get advantage is actually by switching codes. So that's an example where we can switch between the 2D color code to the 3D color codes. And actually, in the first one, we actually get this kind of Clifford transversally. And then in the 3D version, we actually get these T-gates that we can implement transversally. So by switching between them, we can actually get all of this set and get a universal set of gates that we can implement transversally, right? And so this could be a really great advantage if we could get this kind of interesting set of gates that are easy to implement in GKP, okay? So can we get these advantages? And the answer is yes. And I will show you a few examples at the end. But first, we will go back to what are really dynamical codes. I will present GKP code, just a reminder for everybody, in the lattice theory. And I will combine all of that into the dynamical code in the end. Okay, so let's start with dynamical. For a general stabilizer code, we can use a number of pairs of non-commuting pairs, I will say here. And so Z1 and X1 will anti-commute, but they will all commute with the rest of the set, right? And so these, I just write them as X and Z, but they can be non-local, so they can be a combination of any X and Z on other qubits. We can split them in three categories. So the blue one on the top left will be our stabilizer. On the right, we will get the generation for the logical. And lower left, we get the stabilizer, which takes us from error space to another error space. Okay. And so this code, the stabilizer code, is defined totally by the group S. And we get the set of non-trivial logical operation from the generation of these orange operator there. Okay. And so what we mean by dynamical code is actually a sequence of stabilizer codes that through measurement takes us from one code to the other. Okay, so I will show more example there, but mostly what we need to understand is how does this code evolve under a specific measurement, right? So I will just go through what kind of measurement we can do. So the first one is actually just measuring a stabilizer, which we will use for stabilization in general. And so this does not change the codes, right? You just get a syndrome and we can apply back some correction. The second, and yeah, the group is unchanged there. And so the second kind of measurement that we can do is actually measuring a logical operator. And this will reduce the size of the encoded space. And so we can use that to either initialize the code or actually read out the code. So this will be the second type of measurement that we can do. And yeah, we had a generator to the stabilizer group doing that. The third type of measurement that we can do in this kind of code is actually measuring a destabilizer, which is actually an operator that is outside of the code. So that would be a little bit weird to talk about this, but we actually can see it in a different way. So here we will kind of replace a stabilizer with a destabilizer in this code. And a different way I would like to see it, and maybe for you to see it also, is that we go through this kind of reverse measurement. It's not a real operation here. It's just like an idea to be able to understand what is going on. We come back to this kind of qubits that is unused, and then we measure the other non-commuting operator in this pair, okay? So we kind of need to think back a little bit and then go do this measurement. Okay, and this brings us to the idea of a gauge qubit, which describes subsystem codes in general. So what are subsystem codes? They are just stabilizer codes where we don't use all the logical space that we could, right? And so here, for example, I have 4 logical qubits, but I can use only 2 of them, and the other 2 I don't really mind. And so this new code is kind of defined by this gauge group, which is the combination of these red operators and the blues operators there. And we can define the different kind of logical operator on there. And so the logical that only apply on the orange or only apply on the red ones. And so with this tool, we can actually understand code switching, okay? And so let's say I have a stabilizer code defined with just 2 pairs here. And then I decide to measure the operator dx. So it's kind of in between logical operator and in between the stabilizer. And so when I will do this measurement, I can just multiply one of the logical operator by a stabilizer. I can always do this. It doesn't change the shape of the logical operation. And then I can just find a new destabilizer for these new codes that makes it so that now dx is part of the destabilizer set, right? So when I will measure this new operator, I can just think about it as a new qubit and then measure back. So with this final table, actually what we see is that the code is actually different from the one we started with. And it's actually just local teleportation from the logical qubit that we had to a gauge qubit that we had on the side. Okay, and so we could finish the whole teleportation to the gauge qubit by just measuring here the Z operator that is no longer an actual logical operator in this code. Okay, so to understand this kind of measurement, we need to always place the new measurement that we're trying to do and the initial code inside the same code, which here is the subsystem codes that we go through. So subsystem code are actually like what defines this kind of moving along in this dynamical code. Okay, and now I can introduce GKP code and try to bring these ideas to the top. Okay, so GKP code are actually translation symmetries code. Okay, so generally we use displacement. I use translation. These are just scale version of it, just to make it easier for me. And we get the mode operator, mode vectors, if you want, and the anti-symmetric matrix, the form, right? And so these kind of translation in phase space, they will commute, but with a certain condition, we call it a braiding relation. And so for specific choice of these vectors, so the vectors are translation, so this is not phase space. Like nothing I will show here is phase space. These are just arguments that I will input into these translation, and they will represent translate operators on phase space, okay? And so they commute if they define a space that is an integer here. Okay. And so if I take a set that they all commute together, all right, I can take any combination of them and they will also commute together, right? And so they define this grid in this space that it's, again, it's not space. I know it looks like it, but it's not. And so it defines a grid. And we can also define this A matrix, which is a symplectic graph matrix, and it defines these commutation relation, all right? And so this matrix, we can actually find a canonical form for it, which is this kind of anti-symmetric matrix. And here, D is a diagonal matrix made of integer, okay? And actually, it defines the QDIS decomposition of the codes. So here I get D, which is diagonal 3 and 2. It means that we actually get a qubit and a qubits in there. Okay, and so we can, in this form, we can actually split every vectors that defines the grid into pairs of 2 by 2. And so each of those will define one qubit in there. Okay, so we're kind of finding this form of 2 by 2 non-commuting pair slowly, like it's going to appear. And so yeah, the non-trivial logical operator are all the translation that commutes with it. I don't want to spend too much time here, but mostly what it creates is a new grid, right? That it's included in the first one. So it's, of course, like all stabilizer commute with each other, but there's more translation that actually commute with the stabilizer. And that's the grid that it shows here. And so we can split this bigger grid into cosets, and each coset which actually represent one logical operator in the code. Okay. And yeah, so we get a generator for this like included lattice. It's related through the gram matrix there. Okay. And so now we're ready to actually construct this tableau that I was showing at first. And so the two stabilizers that we have is true generator for the lattice lambda. And then the length of the vectors actually fixes through the gram matrix the size of the encoded space here. So I get this kind of do non-commuting operator. Okay, so this grid is fully, this lattice is fully described by these two stabilizer, and then we can actually find the set of non-trivial logical operator. And finally, these are the little square on the right is the space of displacement that I can actually correct back through measurement of the, okay? So now we can actually go and figure out what are dynamical GKP code. These are just a sequence of lattices. And so we will map lattices to lattices through translation measurement. Okay. And so to do that, exactly as the same for qubits, we need to actually understand what are the different kind of measurement that we can do on GKP codes. Okay. And what they do on the code. So first, again, if I take a measurement of a translation that is part of the lattice that I was already stabilizing, then it doesn't change anything, right? But if I take now a logical measurement of this grid, so now a yellow dot on the right, what it will do is I will actually find this I will measure this new operator. So this orange one becomes blue, and we kind of can see this, this new destabilizer that kinds of appear, but was not usually there at first. But when we reduce this lattice, we actually find that we come back to a normal stabilizer that does not encode any information in the end. Okay. So to understand a little bit more this kind of destabilizer formalism for GKP code, we actually need to understand how to go back, right? And so how do we go back in this kind of stabilizers? We actually need to scale up the lattice. Okay. So if I take the stabilizer on the right and I apply this kind of scaling matrix, I can find back the stabilizer of the first code. And so doing that, I can, by scaling the first vectors, I can create more space for logical operator and create more space for like these gauge kind of qubits for GKP codes. And so through an example, this is just a square GKP as we will find it. And so let's just take two generator for this matrix. The logical operator, this is a qubit, so we just divide them by 2, which is the dimension of the qubit. And then we can find 2 logical operator for them, 2 generator, right? And so let's scale this code by 3. Okay, let's just take it at that. And so the logical lattice, which actually be divided by this exact same number. And so we'll find 2 pairs now of generators for this lattice. And actually we get as much pair of generator as there are prime factors in the D here. Okay, so by adding these kind of 3 factors, I get another prime and I can add a pair. And so I find another code that is actually contained in the first code, right? And so we get this kind of structure of grid that is included in the next. And so we find this kind of code that is included in the bigger one. And so these are exactly what we were looking for gauge qubit in the case of GKP codes. And so they are just codes that are scale, which we can encode more logical pairs in there, right? And so I can define a gauge lattice, a different kind of logical operator on these kind of codes. And of course, distance. Okay, so now we come to the case of code switching, which will tell us how we go from one code to the other. So let's say that we measure some fraction of a stabilizer, which is not a logical operation at first, so it's outside of the code. In this example, it's just a little cross. I don't know if everybody can see it, but so we have this code and we try to measure this kind of in between the code. How we can see that is that we actually, it was a bigger code, so a scale code that we actually measured before. And so going through these reverse measurement, we can see it as it's included in a bigger code. So now in this code, it's the measurement and the first stabilizer is included. And then we just do the measurement. And like through this measurement that is outside of the first code, we see that we have actually not lost any logical operation through this thing, but clearly the code has changed, right? And so through this measurement, we do this kind of upping, and that's how we make the code go forward in time. So we have like space-time codes, okay? And so that brings me to some application, which maybe will be more interesting. So this is the first example, like the most trivial example that I could find, but it is still very interesting. It's what I call the square hexagonal dynamical GKP code, is that actually in the square code and in the hexagonal code, we get rotation gates, okay? In the square code, it's Adama, and in the hexagonal code, it's kind of Adama time phase gates, okay? But we get both of them just by rotation of the oscillator. And in superconducting in general, it's just doing that by clock fixing, which is like you don't do errors then, right?
What's clock fix? I don't know.
It's just changing, like waiting a little bit more before doing the operation. So you don't do an operation to get those. So they're virtual. And so if I can switch in between the codes, then I can have access to both of these. And then I can implement all the 1-qubit Clifford gates like for free, right? And so the idea is that using local teleportation between GKP codes, we can actually go from one code to the other, but we need to be a little bit like intelligent about doing this thing because we want to actually learn information for error correction also, okay? So here I present like a sequence of measurement that actually gets you to stabilize the information, but at the same time, switching between the codes, okay? And so this code is actually, we switch between the square and the hexagonal code every 2 rounds. So we go to the psi here, goes down to the hexagonal one and comes back up every 2 rounds. And then we get a full round of error correction every 4 measurement rounds. So these orange boxes are actually measurement of these X operator, okay? And so in this case, we get actually an advantage, a few advantages, is that these measurements are actually smaller than the one we will do if we were to measure X square or Z square. So we kind of get this reducing in weight of the operator. We get all 1-qubit Clifford virtually, and we're also doing error correction at the same time of doing that. So it's kind of all inclusive, and then it looks like perfect to be included in a concatenation code because now you can do all single qubit free. A second example I would show is this is just a circuit for like 2-qubit gates teleportation, but actually when we do it with GKP, using this kind of technique and following where the error can happen, this circuit actually you can kind of correct error at the same time that you're applying the gates. And this is just by adding 1 and theta. So we can create this kind of, we can reuse the idea that we had for qubit codes, but we can reuse them in GKP and actually get an advantage in error correction at the same time, because we can find a correlation between errors between the added bond that is in the middle and then the 2 others. And by doing the measurement, we can actually correct more error there, okay? And so I will finish my talk with this kind of final example, but also kind of different than what I showed before, is that what happens if I do not measure a fraction of a stabilizer, okay? So actually I cannot find a code, like there will be no scale code that will include both the measurement and the first code that I had. So here the cross is just like, let's say, it's irrational compared to the grid itself. And so let's try to add this new translation measurement in this generating set, right? So for no multiple of S2, I can find them commuting. So I actually need to move this generator out of the stabilizer group. And so the stabilizer group is now only generated by 2 measurements that is actually in the same direction, but one is a natural one, and the other is irrational. And so what we get is that we generate the whole translation on one line here. We can understand that through the Lafayette theory, but what it means is that actually we have a projection on exactly only one value of omega S1, which means that actually we do not encode information, but also that it's corresponding to a homodyne detection in the platform. And so through this kind of measurement and translation, we can actually understand homodyne detection. And so it means that for all platforms with GKP, we can understand them through Tableau, which means that we can do efficient simulation of, yes, Gaussian operation, but also all kind of measurement like translation and homodyne, and also condition operation on these measurements, right? And so that's pretty much what I had. I would just leave you with the summary and outlook about all these results, and don't hesitate if you have any question. Thank you. Yeah.
Have you thought about how this plays with like finite energy approximations to the GKP state?
All right, so we're actually doing simulation right now just to figure out how it works. But like what we use in general for finite energy is that we sandwich the translation between these kind of envelope terms. And so it does not change the commutation relation between the operation. Like we get the same thing for finite energy version of the stabilizer. And so it should work almost all the same. It's just like, is it performant? Like, can we actually do it efficiently?
But presumably you won't have these like very sensitive, like number theoretic, like irrational things anymore, right?
Of course. So what will happen is that here in general all right. So here the choice of beta, it's like, it doesn't change anything, but like when we will get to like, it's how much can you approximate an irrational number with this kind of combination. So if it takes you a lot of them, then it means that the first stabilizer that will kind of respect the condition of commutation will be very far. And so it will almost approximate the homodyne detection anyway. So it's kind of, you will make an intelligent choice of beta there to make it work.
In the middle of your actually this implementation, you needed to go from d equals 2 to d equals 6.
Mm-hmm. But
how do you apply this scaling up? How do you go to higher in the middle of your circuit? How do you go to higher dimension?
Okay, so we never go to higher dimension. It's just an image to be able to understand what is going on behind it. Because if we stay in the first code, like we are actually measuring something that is outside of the code, so we cannot understand how it evolves or what is doing on the code. So we actually need to go to a bigger code, like imagining this bigger codes that we go through to actually find what happens. So like we never go to this bigger code, like we never actually have the states there, but it tells you how to understand this evolving through the code, if it makes sense. Yeah.
Thanks for the great talk. Super interesting. So a lot of this, you talk about measuring stabilizer operators or logical operators, and it's all very like nice propagating this through in the ideal case, but these operators aren't mission, right? You can't directly measure them. They're unitary. So how do you map this into a practical scheme then in a single shot case where you have to then do a permission measurement that represents the logical space or the stabilizer space?
Actually, thank you very much for this question. I was like waiting for that one. So most likely, like in opticals, you can kind of get your way with homodyne detection and kind of get one-shot measurement. In superconducting platform, for me, I think this scheme will work with kind of a BAT interaction that brings you close. So like these autonomous error correction, like SBS protocol, you can actually get the result not exactly on the face, but like good enough that it still works. Like
yeah, cool. I think with like so I'm working on some stuff at the moment, but just doing homodyne measurement, you can't like single shot pull out logicals of like say the hex code. You'd have to like, I don't know, supplement it with a resource state or something. I don't think we can talk about it.
Yeah, but still like a resource states, you can prepare it another way. Like you can prepare it before the whole computation. Right. Yeah.
Or again,